coming? No, it has started from again beginning. Nothing.
Ah, it's coming. Great.
So 24th will be the practical. They are asking me, sir, if we will see those things in the practical, that how we will purify and but they have to have the laptops. So आज ही बोल
they will bring you.
But internet connection also.
So next speaker agreed, no problem.
Who?
Kishore.
Okay.
Okay, all are here. We'll continue the lectures.
So these are the sequence alignment tools: BLAST, FirstW, Beauty, Cluster W Mega, which is used to do alignment. Now, I got many inquiry during the tea time that how to do really those things, how to do this alignment, how to purify the sequence, to remove the vector and other things. So, we will have a practical on this on 24th. Sir, on 24th? So, we will have a practical definitely, where you will bring the laptops and we will show those things how to do. So, starting with the BLAST, it is not bomb blast, it is the acronym of a big thing which is called Basic Local Alignment Search Tool, that is the BLAST. So, it terms tells us that it is doing a local alignment. It is not taking the entire sequence, it will just randomly see that the region which is showing a stretch of the region which is showing highest similarity or identity. Based on that thing, it will tell you that how much similarity is there. So, what it does? BLAST is the algorithm used by a family of 5 programs that will align your query sequence against the sequence in a molecular database. So, whatever sequence you will give, it will do a alignment online tool actually it is. So, if you just give your sequence and you there is a button called BLAST, you do the BLAST and then it will do with the 5 different programs and it will tell you with which stretch of sequence of your sequence is matching with what sequence. Statistical methods are applied to judge the significance of this method, that which one will be the most significant and which one will be the least, and alignments are reported in order of the significance as estimated by the applied statistics. So, the most means confident sequence or significant sequence will be giving you the first, then one by one it will come. So, BLAST actually has different programming. This is the BLAST N, which compares a nucleotide query sequence against a nucleotide query sequence database. So, if you want to do, if you want to give that software the DNA sequence, it will align the DNA sequence of different organism, different genes deposited in the database. So, it is called BLAST N. BLAST P, it compares amino acid query sequence against amino acid query sequence. So, if you want to analyze the protein sequence, the amino acid sequence, then you have to give the option BLAST P. So, in the BLAST these options will be there, BLAST N, BLAST P, like that. Then third one is BLAST X. This compares the 6-frame conceptual translation product of a nucleotide query sequence against a protein sequence database. So, you give the nucleotide sequence, what it will do? It will conceptually translate that protein sequence into 6 frames, 3 frames from one strand, 3 frames from another strand. So, total 6 frames it will generate the amino acid sequence. Then all these 6 frames amino acid sequence, they will searched along with the protein sequence database. So, it is the nucleotide protein sequence matching. Next one is T-BLAST-N, it compares a protein query sequence database to the nucleotide database. So, if you have a amino acid sequence, you want to know that particular protein is coming from which gene. So, for that you have to do T-BLAST-N. So, now in this case you have the amino acid sequence, you want to know what is the corresponding gene for that sequence. So, it will do the opposite thing, it will compare the protein query sequence against the nucleotide sequence database, and then it will show you the significant matching. So, this is the how it looks like. So, you have to give your query sequence here in the things, and there will be one option called blast. So, it will blast and this will generate the results in this. So, you can see they will generate the result as maximum score, total score, query coverage and E value. This query coverage means in the entire sequence how much region it has covered for the analysis. Okay? And this is the score. Based on the score, actually they have organized that which one will be the highest score. That means this has the most searched similarity is much more with this particular sequence. And the E value, if it is 0 means the exact sequence you have, and if it is less, that means it is more probable that this sequence is with the homology with that sequence. So, these are the this is the result which the blast will actually show you. Then what we actually know from the blast? We know that sequences that share similarity with the query sequence, and it helps us to retrieve those sequence. So, blast is only for these two purpose mainly, that just at a glance to know what sequences my sequences is showing similarity, and then you just retrieve those sequence from that blast analysis. Clear? But you cannot do a quantify the sequence similarity as it is the local alignment. You cannot quantify the sequence similarity, though blast also generates one column which is showing similarity, this much percentage, that much percentage, but that percentage is only the region which it searched. The rest of the region which is not taking count, it will not tell you, and cannot tell us about the relationship between those sequence. As it is only local alignment, it cannot tell you the entire relationship of the entire sequence. To explain that thing, how I am trying to tell that, suppose this is the sequence result with your query, this is the subject which is deposited in the database. So, this is your query sequence, and in the deposited sequence this has matching, or this is the deposited sequence, your query sequence is matching in this at the dependent stretches. Okay? So, in the entire query, in the entire coverage is very high, because it is almost taking the entire sequence. And if in this case you see here it is showing 92% similarity or identity, because it has taken out of 373, 346 is the identity. So, that is okay, because it is almost taking the entire coverage, but it has not totally coverage, it is not totally 373, some nucleotide it has not taken, but if you take that also, that will not change very much this value. Okay. So, in this case if it is 92%, it is we can very comfortably tell that okay, 92% means query coverage is also very high, and the similarity also high. So, these two sequence probably the homologous sequence, but this sequence, this kind of things may situation too, less query coverage, but high sequence identity. For example, these are the two sequence we have taken. So, this is the deposited sequence, and this is in the entire sequence only this stretch is matching with this, and here you can tell this is also showing 91% similarity, but the entire sequence which you have given, suppose it is 373 nucleotide, it is only showing 84 stretches of sequence out of the 373 nucleotide, only 84 nucleotide stretches is showing the similarity, rest of the things are not showing. But blast will tell you again 91% is the sequence similarity, but it is only within that stretch which is analyzed, not the other things which it has not analyzed. So, just by taking this value, the similarity or identity value, both the things, that means same. The first sequence which it is showing the coverage 100% and similarity is 92%, and here coverage is only 10% or 5%, but identity is 95%. You cannot tell that both the things results are same. Can you tell? So, you cannot tell by this way. So, in the earlier case, those two sequence may be homologous sequence, but in this case they are not homologous sequence, though it is showing in this stretch it is showing this much percent similarity, but they are not homologous sequence. Clear? So, you have to take when you do a BLAST analysis, you have to take those sequences where the query coverage is very high and sequence identity is also very high. You take those sequences and then do analysis. Clear? Yes. E value means that not this, the probability of not matching is the E value. So, if the E value is less means probability of matching is more. Okay. Probability of matching is more means there are much more try to be the homologous sequence, and if the E value is high, that means probability of matching is less. Okay. It is inversely proportional.
And in some cases it is minus, in minus, or if it has to be 0 for ideal condition.
If it is exactly matched, then it is 0. Okay. Otherwise, it will have means always it is written 10 to the power minus 3. It is the log value actually, that is why it is inversely proportional. Okay. This E value is the log value actually, that is why it is inversely proportional. So, it is clear that that means from the BLAST never, I have seen many students just take the identity value from the BLAST and tell that this is the sequence identity. You have done? Many students has done like that. Just take that sequence, the whatever BLAST result is there, the last column is a percent identity, take that identity value and tell that this is the sequence identity. No, that is not the sequence identity, because that is the local alignment sequence identity. So, to understand the real sequence identity, we need to do global alignment, not the local alignment. Local alignment only to have a initial idea that with which sequence our sequence is showing similarity and retrieve them. And then after retrieving, you have to do a global alignment to exactly know what is the percent of identity or percent of similarity. So, global alignment is done in 3 different steps. The first step, it does a quick pairwise alignment. What the BLAST has done, that is the local alignment, but it will do a global pairwise alignment, 2 sequences at a time. They do pairwise alignment, then they form a guide tree, a relationship tree they will form, and then they do a progressive alignment following this guide tree. So, this is the kind of condition if you do. So, you can say this sequence with this sequence, they have done a pairwise alignment, they generated a score. Again this sequence with another sequence, they have done a alignment, generated a score, and after that they do a progressive alignment. So, they found that, for example, if you have given 30 sequences to do analysis, they found number 21 sequence and number 6 sequence, they are having highest score. So, they took these 2 as one group like this. So, they created one group with these 2 sequence, and then they analyzed with this group with other sequences, that with this group what group is showing much more close similarity, and again they generate another scores. So, based on this scores, now they reveal this sequence as value, percentage identities, as well as you can generate a relationship tree. So, it will, so ultimately it will tell you this kind of alignment, and then it will generate a kind of percent sequence identities, and it will generate a relationship tree. So, this is called the molecular phylogenetic tree. So, what is this molecular phylogenetic tree tells actually? So, it looks like this. Okay? So, what is these things actually? So, there are 3 components. One is this kind of area from where different branches are coming out.